This is a quick video cast of Thermochemistry Chapter 5, more practice before you take your retake test. I'm going to go through each one of the problems quite quickly, showing my work, and then attempt to answer some of the fallacy or types of pitfalls that students fall into for each one of the problems. First of all, determine the value of the standard enthalpy change for the combustion, and it gives you two reactions, and it wants you to find this reaction. So first reaction right here needs CO in the front of it, so flip this one, which means you flip the enthalpy change. Second reaction, leave it the same because you need carbon on, carbon to cancel with the carbon on this side, and you need oxygen on this side. Then when you combine the two reactions, you'll see that the oxygens cancel. 1/2 cancels here, and you end up with a half over here on this side, and the carbons cancel on both sides. And when you add the two reactions together, you have to add the enthalpies together to get the overall reaction right here of negative 283 kilojoules per mole. Question number 2. This one says, look at the reaction below, determine the enthalpy change for the reverse of the reaction. When you reverse the reaction, you simply reverse the sign of the enthalpy. So just take 264 as a negative and make it be 264 positive kilojoules. In letter B, it says determine the enthalpy change for 1/2, 3/2, and NF3. And to get that, you had to multiply this reaction by a half. So just take the enthalpy then and multiply it by a half. So you take a half times negative 246, and you get negative 123 kilojoules. Letter C says calculate the standard enthalpy change when a 0.256 mole sample of NF3 is formed. In this reaction, it tells you how much energy is released when 2 moles of NF3 is formed. See how there's a 2 in front of here? That's 2 moles for every 264 kilojoules released. So simply take your 0.2656 moles of NF3, and for every 2 moles of NF3 that are formed, 264 kilojoules are released. So divide by 2, multiply by 264, and you end up with negative 33.7 kilojoules released for that 0.256 mole sample. Moving on, problem number 3. The first question asks you to write the complete combustion reaction for 1 mole of hexane. I'm assuming that it's 1 mole of hexane. So here's hexane. It reacts with oxygen, forms carbon dioxide and water. Since there's 6 carbons here, balance it alphabetically. I always recommend carbons, then hydrogens, then oxygens. You need 6 carbons. Hydrogens then, you need 7 times 2 gives you 14. And then since the oxygens end up being an odd number, 12 plus 7, 19, you need 9.5 oxygens right here to balance that equation. On the basis of the information, calculate delta H for the complete combustion of hexane of 10 grams, 1 mole of hexane. So your first goal is to convert 10 grams to moles, and there's 86 grams in a mole, so that's how many moles of hexane you have. Then you can take and read that it says per mole of hexane. If you read it carefully, it says for the complete combustion of 1 mole of hexane. So to do that, you know it's how many kilojoules there are per mole. Since it's per mole, it means divide it. So take your energy and divide it by the number of moles you have, and now you have kilojoules per 1 mole, because remember, any number written over 1 is that number. And so it's 7,093 kilojoules per 1 mole. Then letter C, it says 0.4 mole sample of hexane is combusted in a bond calorimeter. Calculate the amount of heat released to the calorimeter. So it's 0.4 moles now. So since there's 0.4 moles combusted, multiply that by the 7093, because that's how many kilojoules are formed when 1 mole is combusted. So 0.4 times 7093 gives you 2,837.5 kilojoules. Part 2 then says it's in a bomb calorimeter. And so it asks what the temperature change is of that bomb calorimeter. And since it's 0.4 moles, you know that's the amount of heat that's released or heat that's created. And then it gives you the heat capacity in the question. It says the heat capacity is 4.52 kilojoules per degree Celsius, and you multiply that by the temperature, and that's the bomb calorimeter equation. Plug and chug for this one, divide by 4.52, and you end up with a 627 degrees Celsius temperature change. It could also be in Kelvin. That would be absolutely fine as well. Number 4, it says look at the reaction below. The standard enthalpy change for the reaction is 10 kilojoules. Fill in the value for the table below. So for this one, you need to know that it's enthalpy of the products minus the enthalpy of the reactants gives you the overall enthalpy of the reaction, which is 10 kilojoules per mole. So here's the equation. Enthalpy of the reaction is equal to products minus reactants. Don't forget to add them together. 10 kilojoules is the overall enthalpy of the reaction as given in the problem. It's these two added together minus those two added together. Oxygen, of course, is in its elemental state, so it has an enthalpy of 0. That's why it's not given in the table right here, because you should know that. And then 30 for NO2, 34 for O3, and this becomes X. Solving for X, you end up with negative 14 kilojoules for the enthalpy of formation of NO. Technically, there'd be a little F down here and a little circle up here, meaning that it's the enthalpy of formation at standard conditions. Going on to number 5 now, it gives you 3 questions, and it gives you these combustion reactions. It says in the empty box, write a balanced chemical equation for the complete combustion of 1 mole of CH3OH. Assume the products are in their standard states. So for this one, 1 mole of CH3OH plus oxygen makes CO2 plus H2O. You now need to balance it for 1 mole of this. So you'd need to have 2 H2Os over here because you need 4 hydrogens, which means you'd need 3 halves O2 right here to go with the O to make sure you've got 4 oxygens on this side and 4 oxygens on this side. Then in letter B, it says on the basis of your answer to part A, determine the enthalpy change for this reaction. To get this goal reaction now, you need to use the reaction you wrote in A plus these 2 reactions, add them together to get this. So I always like to work from left to right and just make sure that I have the reactants in the correct place and the products in the correct place. And so the first reaction is carbon plus O2 goes to CO2 because I need the carbon right here on the left-hand side. The second reaction, I flipped the reaction that I did up above, and that was this reaction that I didn't write in the box, but it's written right up above here. And when I flip the reaction, I flip the enthalpy change to be positive 730. And then lastly, I'll toss this reaction in here in the top because I need some H2 in the reaction as well. And the H2 plus 1/2 O2 gives me H2O, which is negative 290. I add these together, and when I do this, I'll have carbon and oxygen here, 2 H2O, CO2 and H2, and a 1/2 O2. That's all the things on the left-hand side right here, written right here. And I'll have all the things on the right-hand side written over here. And then I can cancel a number of these things. The O2 cancels here. I've got a 1/2 O2. That'll cancel with my 3 halves over here. The CO2s cancel. One of the HOHs cancels here. The HOH cancels here. CO2 cancels, and I'm left with my goal reaction right here. Since I added them together to get this overall reaction, I simply add the enthalpies right here, and I end up with 50 kilojoules as my overall enthalpy for that reaction. This is called a Hess's Law problem. Letter C, it says write the balanced chemical equation that shows the reaction used to determine the enthalpy of formation of 1 mole of CH3OH. Since it says formation, it means it's formed from its elements. And CH3OH would be formed from carbon, oxygen, and hydrogen. And carbon in its standard state is just C. Hydrogen in its standard state is H2. And then oxygen in its standard state is O2. And I need to form 1 mole of CH3OH. And so I need to balance this reaction. So I'd need 4 H's, put a 2 here. And I'd need 1 O, so put a 1/2 right here. Lastly, letter 6, or number 6, an experiment is performed with standard molar enthalpy of neutralization of strong acid by strong base. Here's my strong acid, here's my strong base. What equipment is needed? Find the enthalpy of neutralization. I'd be using Q is equal to MC delta T. This would be my enthalpy, and then I'd probably want it per mole because it's enthalpy of molar enthalpy. So what equipment would be needed? Well, I'd need to find the mass. I'd need to find the temperature change. And so my measurements would have to be a graduated cylinder to measure out the volumes of each, the acid and the base. If I knew that the density was the same as water, which is 1, then I could calculate the masses of each. I could alternatively say that I'm going to mass out each of the solutions. I'd use a pipette or a burette or a graduated cylinder to measure that. I'd need to measure the temperature, so I'd need a thermometer. And then I'd need some type of reaction container, probably like a styrofoam cup like we used for a calorimeter. Alternatively, I could say a balance if I was going to actually mass the volumes of the liquids rather than assume that their density was equal to 1 gram per milliliter. Secondly, it says what measurements would need to be taken? Well, look at the equation. I'm going to have to measure the temperature final and the temperature initial. I'm also going to have to measure the mass or the volumes of each one of these things. So temperature initial, temperature final, the volume of the HCl or the volume of the NaOH. Alternatively, I could say the mass of each one of these acids or bases. Letter C, when performing the calculations, describe how the resulting data would be to determine the standard molar enthalpy of neutralization. Well, I'd calculate H from MC delta T using the masses of the solutions, the specific heat. I'm assuming it's probably going to be equal to water because they're aqueous solutions, and my temperature final minus temperature initial. And then I'd take this delta H and I would divide it by the moles of my acid if I wanted the molar enthalpy of neutralization of the acid, or my moles of base if I wanted the enthalpy of neutralization of the base. So divide it by those two. And then lastly, letter H, there was some error. What are likely causes? Well, most of them have to do with the enthalpy or heat being lost to the surroundings, lost to the calorimeter, absorbed by the calorimeter, or lost to the stirring mechanism or the stirring machine or something else. This is a quick overview of the Chapter 5 more practice test.